Okay guys, as I had mentioned, I'd like to move on now. Now that we know something about vectors, I'd like to talk a little bit about a very interesting subject, which is the motion of projectiles. So this is projectile motion. So let's start off by thinking about what a projectile is. This is a familiar word, but what is a projectile? We have a pretty specific meaning in physics for what a projectile is, and we think of it as any object that's being projected or is moving through space where the only force acting is gravity. So object moving through space, or I'm just going to say moving, acted upon only by gravity. So specifically, the sorts of things that we're ignoring then is like air drag, for instance, any air effects. So if you, in the presence of air, you get all sorts of things that make a would-be projectile not behave like a projectile. So obviously a bird flying through the air isn't a projectile, or an airplane flying through the air isn't a projectile. There are all these other forces of thrust and drag and lift and so forth, or even if you just hit a golf ball or throw a baseball, you're imparting spin on the ball, and the spin causes interesting effects, something called Bernoulli's principle, that causes the ball to maybe move either in the X or Y direction in a way that it wouldn't without the air effect. So we're really thinking about an object moving where there are no air effects whatsoever, and we'll consider that for our purposes to be a projectile. And I'm just going to sort of introduce you. We'll get into it in more detail in class, but I just want to introduce you to three basic rules. So 3 projectile rules. And we can apply these 3 rules to understand the motion of any projectile. So let's break it down here. 3 rules for projectile motion. The first rule is describing the motion of a projectile in the x direction. And if you think about it, we haven't really talked about forces yet, but in the x direction, there's nothing in the x direction that's pushing or pulling the object at all. So if I were to throw a ball on Earth, we're ignoring air resistance, but if I were to throw a ball, there's nothing moving the ball or pushing it side to side. And so the x velocity, very legible, the x velocity is constant. Since there's no force acting in the x direction, the x velocity remains constant throughout the motion of the projectile. But in the vertical direction, in the y direction, there is a force, namely gravity, and so the y velocity is going to change, and the y velocity is specifically going to change at the acceleration due to gravity. So changes at a rate of negative 9.8 meters per second squared on Earth. Okay, so here are our first 2 fundamental rules. So here, the x velocity is constant, and the y velocity changes at this value, the acceleration due to gravity, right? And this is constant again because there's no x force. There is acceleration in the y direction because there is a y force, gravity. The third rule is actually a pretty kind of in some cases can seem to be a pretty remarkable rule. I'm just going to throw it at you right now, and then I'll try to prove to you that it's true in class, and it's kind of dramatic, and that's that the x and y velocities are independent. So x and y motions are independent. And many of you are probably saying to yourself, that doesn't sound all that remarkable or interesting, but there are some consequences to this that are somewhat surprising. So we'll go over that a little bit in class. But for right now, I'd like to just introduce projectile motion by thinking about a very simple example of projectile motion and instituting these 3 rules to our example. So here's the example, really pretty simple example. Let's imagine we've got a cliff here. Okay, and here's the ground underneath the cliff. Let's see if I can make that a little bit better. Here's the cliff. And here's the ground underneath the cliff. And here I am, I'm on top of the cliff, and I'm going to throw a ball out. Here's the ball, actually, yeah, we'll do it white, that's fine. Here's the ball. And I'm going to throw it out with a velocity. I'm going to give it an x velocity of, here's the velocity. So it's, I should mention this. I'm imagining that I'm throwing it completely parallel to the ground. Okay, so I'm giving it no y velocity. I'm not throwing it up at all. I'm not throwing it down at all. So this angle right here is right along an x-axis. So it's just an x velocity. So x initial here, or sorry, v initial here is 20 meters per second. And it's all along the x direction. And so I want to think about how this ball is going to move through space if I throw it 20 meters per second out. And I'm actually going to invoke the third rule here. I'm going to invoke the fact that these motions are independent. And what I'm going to say is, all right, well, let's just think about the y motion. What's going to happen on the y motion? Let's say that the cliff is 80 meters high. So this cliff right here is 80 meters high. I'm going to call this delta y. Delta y is 80 meters. In fact, I have to make it negative 80 meters. Since we're going down, I've got to say that delta y, the change in y, is negative 80. And let's go ahead and see if we can calculate how far this object is going to fall every second. Let's kind of think about it, break it down second by second. Well, how far will this object have fallen second by second? Let's go back to this. Our rules here. The y velocity changes at negative 9.8 meters per second squared. Well, how could I calculate delta y? I'll make some space over here. Delta y, if it changes, delta y is going to be given by this equation. The initial times t plus 1/2 gt squared. Okay, this is our equation for displacement when there is acceleration. This is an old equation, right? So I've got to use this equation, and I'm going to plug in 1 second and see what I get for delta y. I'm going to plug in 2 seconds and see what I get for delta y, so on and so forth. But before I do that, I've got to think about what the initial velocity is. And you might initially want to say that the initial velocity is 20 meters per second, right? I told you in the problem that I gave the velocity initial 20 meters per second. But remember, I mentioned that this is entirely in the x direction. It's not in the y direction, meaning this initial velocity in this equation is really v initial only in the y direction now, because I'm only thinking about the y direction. And so this is 0 for my problem. V initial in the y direction is 0, because I didn't throw it down at any angle or up at any angle, so the initial velocity in the y direction is 0. So I get 0 plus 1/2 of g is negative 4.9 times 1 squared. So that's roughly negative 5 meters. I'm just going to round it to negative 5 to make my life easier. So after 1 second, it's only gone down 5 meters. So let's say that's 5 meters down. Y equals negative 5. Delta y, I should say. Delta y equals negative 5. All right. Well, what about after 2 seconds? I can repeat this calculation for 2 seconds. 0 plus negative 4.9 times 2 squared. 2 squared is 4. Multiply by this thing, it's going to be 19.6, or about negative 20 meters, rounding. So back to our picture. After 2 seconds, here it is, delta y equals negative 20. And I could keep going. And I'm going to find out after 3 seconds it's gone down about 45 meters. And it's going to take about 4 seconds to get all the way down to the bottom. Delta y equals negative 45. So this was 1 second, 2 seconds, 3 seconds, and then finally 4 seconds. So 80 meters, the ball's going to fall 80 meters in about 4 seconds, according to our calculations. And I'm rounding. It's going to be a little bit different. You know, this is 19.6, as I said, so it's not quite 20, but it's pretty close. All right, so that's the y motion. This is, in other words, this is what the ball would do if I just were to drop it, right? If there was no if I didn't throw it out, if I just dropped it, it would fall, and it falls a little bit farther every second, right? This right here is about 15 meters. This here is 25 meters. Ooh, I made a mistake here. This should read -80. So this is right here, this distance right here is 15 meters. This distance right here is 25 meters. This distance right here is 35 meters. Right, it's going faster and faster and faster, so it's falling a farther and farther distance every second. All right. So far, so good. Well, now let's think about the x direction. I just want to think about the x direction. I don't want to include the y direction at all. And so what I'm going to imagine is, what would happen if I threw this ball and there were no gravity at all? What would happen if I just threw this out horizontally, no gravity? Well, you can imagine it would move, hopefully it's clear to you, it would move in a straight line like this at constant speed, right? There's no acceleration in the x direction, and if there's no gravity, there's no acceleration in the y direction either, so it's just going to move out at a constant pace, right? After 1 second, it would be right here. After 2 seconds, it'd be right here. After 3 seconds, it'd be right here. And after 4 seconds, it'd be right there. And if we wanted to calculate that, since there's no acceleration in the x direction, I can just say delta x equals velocity in the x direction times t. Okay, so this is just with constant velocity, distance equals velocity times time. In other words, if I threw it at 20 meters per second, after 1 second, it's gone 20 meters. So this is 20 meters. After 2 seconds, 2 times 20 is 40 meters. After 3 seconds, 3 times 20 is 60 meters. And then after 4 seconds, 4 times 20 is 80 meters. And so what I've done now is I've treated the x and y independently. X velocity is constant, so I used the constant velocity equation. Y velocity changes, so I used an acceleration equation. And I was able to get this picture. So now, if I want to know how this projectile is going to move in the real world where there is gravity, then I just have to kind of match these up. Right after 1 second, it's gone 20 meters out, and it's gone 5 meters down. It's right there. After 2 seconds, it's gone 20 meters down and 40 meters out. It's right there. After 3 seconds, it's gone 45 meters down and 60 meters out. It's right there. And then finally, after 4 seconds, it hits the ground and it's gone 80 meters. And so now I can see these points. And if I went ahead, if I go ahead and try to connect these dots, right? Here it is at 1 second, 2 seconds, 3 seconds, and 4 seconds. I'm going to get something, if I can make an attempt to connect these dots here, I'm going to get something that's going to look like this. That's not that good. Okay, so I think this is a little too far out, right? Here's where it would be after 4 seconds. I'm adjusting my picture to make my point. And so you can see, hopefully you can see that this path now is not a straight line, it's curved, right? It's moving constantly in the x direction, but accelerating in the y. So you get this curved path, which is called a parabolic path. As in like a parabola, parabolic, like a parabola. In fact, I'm going to prove to you in next class that this is in fact exactly a parabola. And I'll try to prove that to you next class with a little bit of math. All right, so this is just a basic introduction. We'll get into some more involved problems, but the keys are these three. X velocity is constant, y velocity changes at the acceleration due to gravity, and you can treat the two independently. Okay, and we put that to practice here. And just to sort of sum this up so that you guys are clear, when we're dealing with the x direction, what equations are we going to use in the x direction? Well, we really only have one equation. Delta x equals vx times t. Right, we're going to use that equation because that's the only equation we have for constant velocity. And again, note that this is just the x velocity. This is just the velocity in the x direction. When we're dealing with y direction, right, we have to use equations that involve gravity. So if I'm talking about the displacement in the y direction, delta y, it's v initial y times t plus 1/2 gt squared. Okay, and this is our old displacement with acceleration equation. I could also, by the way, if I wanted to know the y velocity at any time t, I could say velocity in the y direction is the initial y velocity plus gt. Again, these are not old equations. These are old, or these are not new equations. These are old equations that we've sort of remade. We're calling this delta y and v sub y because we're dealing with the y direction. But this equation is just this old one that we used to call delta x equals v initial t plus 1/2 aat squared. Right? That's one of our old kinematic equations. Right? And we used to just write this v final equals v initial plus aat. That's another one of our old kinematic equations. We're just rewriting them. I'm calling it delta y because it's in the y direction, and I'm saying v sub y because it's the velocity in the y direction. So these three equations we're going to use a lot in this unit on projectile motion. Make sure that you have those. If not committed to memory, then make sure that you understand them pretty well and know how to use them fairly well. We'll go over this more in class, and then we'll get to progressively trickier and trickier problems through the course of the week.